From differential calculus, we are already familiar with the idea of the derivative. For example, the derivative of x squared is 2x. In this example, 2x is the derivative, and we are going to introduce a new idea called the antiderivative. The antiderivative is the function that you differentiate to get the derivative. For example, in this case, x squared is the antiderivative. This entire playlist of indefinite integration deals with the reverse problem. If you're given the function, how do you find the antiderivative of that function? That is, how do we find a function whose derivative is the function that is given to us? Notice that if you take the derivative of x squared plus some constant, you still get 2x. The derivative of x squared plus 3 is 2x, the derivative of x squared minus 100 is 2x, and the derivative of x squared plus c is 2x, where c is some constant. In general, if you suppose that the derivative of capital F is small f, then we can say that capital F is the antiderivative of small f. And we also define a new quantity which is indefinite integral. The indefinite integral is simply capital F plus c, or capital F of x plus c. So the difference between an antiderivative and an indefinite integral is not much. An indefinite integral is just any antiderivative of the function plus some constant. This is the symbol that is generally used for indefinite integration. This elongated s is the integration symbol. The lowercase f of x, that is this one, this is called the integrand, and the dx is just to show the variable with which you have to integrate. So if it is dx, that means we are integrating with respect to x. If it is dy, you're integrating with respect to y, du integrating with respect to u, and so on. So it means integrate with respect to x. As we have already seen, this is the antiderivative, and the c is known as the constant of integration. So the way you would read this out would be the integral of small f of x dx equals capital F of x plus c. Going back, the constant is just to show that there can be multiple antiderivatives of a given function. All of these antiderivatives just differ by a constant. I must note here that it is very important to write the dx every time you perform some sort of integration, and it is also important to write the constant of integration. Let's see what happens if we differentiate both sides of this equation. If you take the derivative of the integral of f of x dx and the derivative of this antiderivative, on the right hand side, the derivative distributes to the antiderivative as well as the constant. Now, the derivative of the antiderivative we simply denote as f prime of x, and the derivative of the constant is simply 0. But as we know, f prime of x is nothing but the integrand lowercase f of x, this one. And so we have concluded that when you differentiate an indefinite integral, you end up getting the integrand. Let's practice using some examples. Now the integral of 2x dx, we've already seen that is x squared plus c. Why is this the case? Because the derivative of x squared is 2x. For the next example, can you think of a function whose derivative is cosine x? That is correct. It is the sine function. But we should also write the constant of integration, and so the integral of cosine x dx is sine x plus c. The next example is the simplest possible integral, e to the x. If you remember, the derivative of e to the x is e to the x, and so the integral of e to the x dx is also going to be e to the x, but plus some constant. Notice that in every single answer, I am writing the constant, constant, really important. In example 4, we are given that the derivative of 2x plus 5 cubed is 6 times 2x plus 5 squared. You know this is the case by the chain rule. And so the question asks, what is the integral of 6 times 2x plus 5 squared? Well, since we know that this is the antiderivative, 2x plus 5 cubed is the antiderivative of 6 times 2x plus 5 squared, we can just write the answer as 2x plus 5 cubed plus c. In number 5, we know from differential calculus that the derivative of arc tan x is 1 over 1 plus x squared. Another way to write arc tan x is tan inverse x. But I'm just going to use arc tan x throughout this series. So, since the derivative of arc tan x is 1 over 1 plus x squared, we can say that the integral of 1 over 1 plus x squared dx is arc tan x. Are we forgetting something? Yes, that is the constant of integration plus c. Notice how I rewrote the integral of dx over 1 plus x squared as integral of 1 over 1 plus x squared dx. It's okay to do this because dx is just something that is multiplied by the integrand. And multiplying the dx by 1 gives you dx. Finally, you can think about what is the integral of dx over x. Yes, that is correct. It's the same as the integral of 1 over x dx. And if you remember, this is the natural log. The derivative of the natural log is 1 over x. I'm going to call the natural log ln x plus c. I'm not going to go into any details here, but just remember, if your argument can be negative, just enclose it within an absolute value. You can now try working through these practice examples. I have tried to order them in increasing difficulty and have color-coded them. The white examples are routine in nature, and the yellow ones will usually require some more thought. I highly recommend not moving on to the next video before working through at least the white examples. So go ahead and pause the video. The answers will be shown in a few seconds. Are you ready? Here are the answers. If you found that you were struggling with the white examples, halt. Now is a good time to go review the differentiation or derivative rules. I promise you that it will be very hard to watch the remaining videos without a firm grasp of differentiation. If you had little to no trouble with these examples, well, then see you in the next video.